We'll start the session today, and our first plenary talk is Christophe Josserand from CNRS, École, polytechnique in Leiden, talking about drop impact and solidification.
Thank you very much for inviting me to this nice conference and journey. Actually, I will speak today about drop impact and solidification. We have had already few talks about drop impact and evaporations, or drops and evaporation. So this is another phase change that has been considered quite a lot these last years. So this is a work that I started about 10 years ago with my colleague Thomas Seon, which is an experimentalist. And we have rapidly been joined by Axel as a postdoc, then Virgile Thievna, Antoine Monnier, Rodolphe as PhD student, and recently Vladimir Salvin as a postdoc. Okay, so what is maybe the general context of studying the coupling between some capillary dynamics, like a drop impact and solidification? So you have a lot of context in environment, and actually there are a huge demand of better understanding how ice forms, ice melt in general situations. So you can see this type of ice cascade in the mountain. You might see in some caves some ice stalagmite or stalactite. Something which we would like to understand more is the formation of this type of large-scale instability when you have the permafrost that is melting and then resolidifying and then remelting. So this is, I think, in Siberia and so on. There are also, and I think we had a few talks about that. There are definitely many contexts in industry. Actually, there is a huge demand this recent year on aeronautics because of ice accretions. And as it has said in the talk on Monday, definitely the certification or the rules for planes has been changed to take into account the large supercooled droplet. So there is again, we have to understand how ice is accreted on airplane, either on the wings or either near the motor. This is actually a problem that has been studied for quite a while on metallurgy. So how you can coat system or create structure using liquid resolve. About ice protection or ice problem on structure, you have these nice wind turbines where to avoid ice they use a real, not at all a clean way to avoid it. And as you can imagine, 3D printing is basically at the end of the day a drop of a liquid, non-Newtonian liquid a priori, that is impacting a surface and then it has to solidify and to create the structure. Okay, we have studied these last 10 years many different configurations, very simple and well controlled configuration like drop impact, where we have observed some cracks. We have also have some rivulets that we see how they freeze. Today I will mostly concentrate on drop impact and actually on this type of shape and actually even more simple how it spreads and also the formation of ice in this system. Okay, so actually freezing is not a young problem. So it's the first time I think it was mentioned in literature, to maybe it's because it's French people that I citing them, is by two guys called Lamé and Clapeyron, so you probably know the name. It's actually in the 1830s, and they wrote a paper as they were, I don't know if you can read French, but they were colonels du génie au service de la Russie. So they were students from École polytechnique, and actually they were graduating from École polytechnique, so they were working for the army, the French army, but they were then sent to head the Russia. So they were working for Russia, and they sent a paper to the Academy of Science. So the idea was to say, can we estimate the age of the Earth just by considering that the Earth is actually a sphere of liquid Earth that is just solidifying. And then if we have an idea of the size of the crust of the Earth, and if we know how a liquid metal or liquid is solidifying because it's cooling, then we can estimate the Earth of the age of the Earth. So exactly, they solved this problem, and they wrote all the equations. They had everything they could do. They had the Fourier equations that was just derived a few years before. And for the final anecdote, they sent this paper to Fourier, because Fourier was at the French Academy. So he reviewed the paper, he accepted it, and unfortunately he died a few days after Fourier. So it's probably the last paper that he accepted at the Academy. So they measured that. They were able to write all the equations. So, and I will speak about the equation that they wrote. Unfortunately, they were not able to solve it. They had everything to solve it, but they did not. So somehow the problem they wanted to solve is something like that. You have solid ice and you have liquid, and you want to know how this front is moving as you impose some boundary condition on both sides. And actually, you probably know this problem much more as called the Stefan problem, because actually this problem was maybe more rationalized in terms of mathematics in the late 90s, and he found the equations, particularly the self-similar equation I will discuss. And it was Joseph Stefan that made few papers where he basically solved mathematically this problem, which is called now the classical Stefan problem. So what is this problem? Maybe you can write it more in detail. So basically you have ice, you have water. Let's take it in the simplest way. You have both diffusive equation on ice and water, but now you have to impose some boundary condition here. And as you know, let's say at first approximation, the temperature at the interface is definitely prescribed. You will say, let's say, at first approximation, this is 0 degrees. Or at least, even if you may have some correction due to curvature or so on, this is a prescribed temperature. So that means that if you want to solve diffusive equation in both sides by imposing the boundary, the value at the boundary, you cannot impose any flux. So the flux, the gradients of the temperature at the interface you cannot impose them. They are given by the solution. And they might coincide or they might not coincide. So somehow, what is the physical understanding of the Stefan condition is that when you solve this problem of diffusion with imposing a temperature here, you have two gradients of temperature in the liquid and the solid phase that are given by the solution of your equation. And that corresponds to two heat flux. First one, heat flux coming from the liquid, the other one coming from the solid. And if their difference is not equal to 0, you have to do something. And what you have to do, it's what exactly we know from the phase transition, you have to solidify or to melt. So somehow the evolution of this front is just the heat equation or the balance of the heat flux, which is that the difference of the heat flux at the interface transform part of the liquid in ice or part of the ice in the liquid. So this is a very simple energy balance, which is the Stefan equation. And in general, if you impose, let's say, constant temperature here or something like that, you usually can find a self-similar solution, which tells you that the height of the ice should go as square root of time. Okay. Actually, we during the thesis of Virgil, which is here, we looked to this problem by taking into account the fact that there is now a substrate. So let's consider the situation, which is maybe the one we will consider more generally today. You have a substrate that is at a given temperature, so somehow the temperature is imposed at infinity in this solid. You have water. You could consider the water as also a temperature at infinity that is given. For simplicity, in this slide, I will consider the temperature of the water is just the melting temperature, but you could consider other things. And you have a small layer of ice that is growing, and you would like to understand how this ice is growing in function of the different parameters of the system. So basically, as I said, you have heat equation in the substrate, heat equation in the ice. You could have heat equation in the water, and just for simplification, I don't consider it here. And now you have to, as you have understood, the crucial things in this type of bounded value problem is the boundary conditions. So at the ice substrate interface, you have the continuity of the temperature. So the temperature is the same on the ice and on the substrate, but you don't know what is this temperature. On the other hand, you have the continuity of the flux. So that means the flux that goes out from the substrate goes into the ice. You cannot do something else. On the other hand, as I told you, at the interface between ice and water, since you can have phase transition, you have basically a temperature which is constant and prescribed, fixed by the melting temperature, and you have this Stefan condition, and since we have negated the flux inside the water, you basically only have that the flux coming from the ice is absorbed by the latent heat of evolution. What is nice of that, it's a very nice problem for students. You can find a self-similar solution of this problem if you start initially with a given temperature for the solid and a given temperature for the water. You have a self-similar solution going at square root of t, and which can be shown. And basically, you obtain a solution like that for h of t, which is a square root of t. And df is a solution of what we call a transcendental equation, or say an implicit relation. Okay. So we can measure that. I don't give you the formula so yet, but we did some experiments. Actually, Virgil did some experiments. So the movie does not look looks a little bit dirty, but actually it's. So we just put water suddenly in contact of a substrate, and you can see how the ice is growing. And basically, you can measure how this layer of ice is growing, and you can fit it by a square root of time, and then you can get experimentally this D effective, this diffusion coefficient from experiments, and you can compare it with the one of the theory, and you have a very good agreement. So this is the experimental measurement, and this is the theoretical one. And just to make sure there is no adjustable parameter, you know all the thermal parameter of water, you know the diffusivity in water, in ice, effusivity, and all this stuff. And basically, we found a good agreement. Okay, so this is one way of ice where we can see ice growing. There is actually another way that we probably know where ice can grow. Let's show you this movie taken, I think, on YouTube. Okay, so why did that happen? Yeah, that's the question. So the water was undercooled, so the water was below 0 degrees. So in that case, we are in a different situation. You were undercooled, or you know that if you can put water still liquid below 0 degrees, and in that case, you are in a metastable state. So if you have some seed to create some ice, you can create. So this is somehow a different way of creating ice. You know, you can still understand that as where is the heat absorbed from. You know, when you have the ice from that is going from the substrate, definitely this is the substrate that cooled the water and so on. In that case, this is the water that is undercooled, and that some heat is absorbed when the ice is going from the small ball here. Okay, so in that case, this is something that also is well known. This is the growth of an ice dendrite inside undercooled water. And again, there are some analytical solutions of that, and actually there was a lot of analytical work in the 80s about that, and they found that it's something which is very similar to the Safman-Taylor instability, in the sense that the velocity of the dendrite as function of the undercooling is there is an infinite number of solutions if you neglect the surface tension. And the one that is selected by surface tension in the one, it makes the relation between the velocity and the undercooling. So again, like Safman-Taylor, there is an infinite number of solutions, and the one which is selected is due to the surface tension. And if you compare the theory with the numerics, with the experiment, so in the experiment you have this relation between the velocity of the dendrite as function of the undercooling, so the melting temperature minus the temperature of the water, and the theory can account for what happens here, but in experiments you see you have this nice experimental shape, and it can be fitted by a velocity of the dendrite that goes like k times delta t to the power gamma with some fitting value for gamma. Okay, so today, after this introduction, I will try to speak about drop deposition with solidification, so how the drop deposit on the cold substrate, then drop impact, how, and particularly I will study how drop spreads on a cold substrate, and I may not have time to speak about splashing, how splashing is affected when you have a drop impacting a cold substrate. Okay, so for drop deposition, maybe I can go a little bit fast, but the question is, was actually already given by some work by Herbeau in the group of Lima and Koldewey in the group of Loser, about what if a drop is deposited on the surface, what stops the spreading of this drop? Can ice stop the spreading of the drop? And what is then the mechanism? Is it because you have crystal of the ice in the bulk that somehow will slow down the spreading? Or may you have some ice that will somehow go to the contact line and maybe stop the contact line? So there was still this question about what makes the drop stop spreading. Okay, so here is the experiment that we have done. So we take a water droplet. So we do all the experiments with water, at a given temperature, and we put it on a glass plate, and we will make this drop slowly contact a cold sapphire. So this sapphire is at minus 30 degrees, to minus 20, whatever the temperature. And then we will look at the spreading. So why do we use sapphire and glass plate? It's in order to see light going through this setup, and particularly using polarizer, you expect to see something if the ice is appearing. Okay, let's look to the movie. So we can visualize the dynamics from the side and also from bottom. So let's look from the side. What is the dynamic from the side? Okay, so delta T is my undercooling. So if I have delta T equals 3.2, that means that my sapphire is at minus 3.2 Celsius degree. You see, so the drop is spreading, and at some point it stops. This is the maximum radius. It has reached a radius at which it stops. If we actually, and we can measure the radius as function of time of the contact line, and also particularly the radius of RS, I mean what is the maximum radius or the radius at which the spreading stops. Let's do the same one at minus 10 degrees. First obvious observation, it does not spread as much. So definitely the fact that there is solidification slows down or stops somehow the spreading. If you go even further, minus 15.5, you see again that it stops before, and you might see that somehow here it looks almost symmetrical, like if the spreading was axisymmetrical. Here definitely left and right are not so clearly, so maybe we may have lost some symmetry. Okay, so we use a work of, I don't know, 20 years ago now, about the spreading of a drop at the contact of in her case it was weighting surfaces. If you just balance, when the drop is just in contact with the surface, somehow because of surface tension you want to expand, and what balance this extension? This is the inertia at first, if you neglect viscosity, and if you just make the balance between surface tension that want to pull the interface, the contact line, and inertia that is slowing down the dynamics, you can have get the scaling that the radius of the contact line as function of time should go like square root of time using, and you can rescale that with a capillary time, inertia capillary time. Sorry. Does it work well? Actually, if you take delta T equal minus 3, delta T equals 3.2 Celsius degree, you have a very nice scaling law, good agreement with square root of time. And we are in log-log plot. Everything happens as if the dynamics of the drop was spreading like square root of time, and in a very rapid zone, you suddenly stop. So as if you expand at square root of time, and then suddenly you are stopped by some mechanism. Let's look to what happens if I change the temperature. What is interesting is as you change the temperature, you don't change the things, but you are just stopped before the minus 3.2 degree. So what is the interpretation of that? The spreading itself is not affected by the solidification, but there is something that makes that at some point the solidification is arresting the dynamics, and we have to understand what is the mechanism, what is the thing that arrests the contact line. But you don't have let's say you don't have a viscous effect that makes somehow that the spreading is slower and slower. No, the spreading is always the same, but it is arrested at some point. So actually, we can measure the final radius, what we call the RS radius, and if you measure this RS radius as function of delta T, you have a decreasing function, as we have seen in the movie. And by just making some algebra, you can make that this RS radius correspond to an RS velocity, which will be the velocity of the spreading radius of the spreading dynamics at this radius if it was not stopped. And if you do that, you can associate to any RS radius RS velocity, which in that case is increasing as function of delta T. Okay. Can we now, with that, can we look to some movies to what happens when the drop is spreading? And now we'll have a view from below. If you have I will show you a movie after that, but I think these figures are better. So this is a view from below of the drop, which is spreading on the cold sapphire. So you see that you have, so here what you see is exactly the contact line of the spreading. So that means what you see in blue is the contact area of the drop that is spreading. So you see a very nice circles, but you can see something here. So something has happened here, and you see that this thing is propagating, and at some point when it's reaching the contact line, the drop is still spreading, but as it spreads, this structure is also growing, and when the structure is basically reaching the contact line, it seems that the contact line does not move that much after that. So, as you can imagine, we have identified that these are ice crystals, ice nucleus that are created at the interface, and these ice crystals, they move, and as they reach the contact line, somehow they stop the contact line. So this is what we seem to observe. So actually, if you look to a movie, you can see that. It's less clear than the figure because we take with the color, but you see that you can see definitely that you see that there is like a race between the spreading of the drop and the crystal. And why is it a race? Let me. First, we can measure. We will not enter in detail. We can show that the crystal actually is moving at a constant speed, which is reminiscent of what we showed about the dendrite. So as a dendrite, this crystal is moving at a constant speed that depends on the temperature difference. So we have a race which is easy to understand in the sense that, maybe I will come back then to that, sorry. Somehow the drop is spreading like square root of t. So the speed of the drop spreading goes like 1 over square root of t. And on the other hand, the crystal is moving at a given velocity. So the race is, the drop can never win, at some point, because the drop is always slowing down because it spreads at square root of t, while the crystal is going at constant speed. So there is always a time at which they will touch. And actually, that's what we have checked. Sorry. We have measured the velocity of the crystal as function of delta t, and you have this curve. And you see that this curve, if you remember, that it's very close to the curve that we had about the RS velocity as function of delta t. And actually, we can compare that. We can plot the RS velocity of the spreading drop with the crystal velocity, and we have a nice alignment on the y equal x line. And actually, we can now plot these two velocities as function of delta t, and we have a nice, let's say, not collapse, it's not full collapse, but basically the RS velocity in black and the crystal velocity are really behaving the same. You have always an overestimate of the crystal velocity because it has to somehow overpass the spreading velocity. What is puzzling, and this is, maybe I will open to that to this point, is that if you look to it's tempting to say, okay, this velocity should be the dendrite velocity of an ice, the crystal growing in undercooled water. If you do that, you should be here. So we definitely have a dendrite that is growing, but the velocity of the dendrite has nothing to do with a full, let's say, a free dendrite in an infinite bulk. Actually, it's much faster. But actually, we can understand that easily. The situation we would like to solve is not the dendrite solution that I show you, but something which is more difficult, and actually we haven't found an analytical solution of that. You have somehow an half dendrite that is growing on a substrate. And why does it go faster? Because when you are in an undercooled liquid, only the heat absorbed by the crystal from the liquid is making you going on. On the other hand, here you have a lot of heat that it can be absorbed by the substrate. That makes you, in some way, much more efficient to develop the ice. So that's why we are not surprised that it's a bore, but still it's a nice mathematical problem to find the analytical solution of that. We haven't found it yet. We have something, but I will not go into the detail. Okay, so I will not conclude on that. I will try to go. So now that we have made deposition, what about drop impact? So deposition is somehow a specific case of drop impact at zero velocity. What happens when you have drop impact on a cold substrate? So again, we start from experiments, and basically we have a drop of water impacting a cold substrate, and the substrate is below 0 degree, and we expect to have at the end of the experiments everything will be solid, but we like to see what is how the dynamics works for that. So the experiment was done to control the temperature. We had a big block of metal that we plunged into liquid nitrogen, and we just make sure that the temperature is constant during one impact. Okay. Let's look to the movies to try to understand what is going on. So here, first movie, this is a drop-in pack at room temperature, 20 degrees. This is a movie from Virgin. So as you have seen, the drop is spreading. I stopped the movie at the maximum spreading radius, where you see very nice structure here. You have like a rim which is already a little bit corrugated, and you have a very thin film of liquid. We are at room temperature, nothing else can happen, so what happens? It retracts. It retracts because the contact angle of the water on this substrate is much different than the one corresponding to the maximum spreading diameter, so it has to retract because of surface tension. If we believe that there will be no defects on the surface, we would expect that it will retract as a circle. It does not exactly retract as a circle, but we have always some small defects on the surface. Let's do the same thing, same drops, same velocity on the same substrate, but now the substrate is at minus 10 degrees Celsius. So you see, I will stop the movie now, basically. It has reached a maximum diameter again, which is, we will see, which is not too far from the initial, the one without solidification. But after that, instead of retracting immediately, what you have observed is some capillary wave that were running through the liquid, while in the same time you can see that you have this small layer of ice. So what happens after you reach the maximum radius, you have kind of a dynamics where you have relaxation of capillary wave of your system, and the contact line somehow is pinned on this ice edge. And then if we run the movie again, you see that the liquid is retracting on ice and retracting in a very nice circle in that case. And if we continue the movie again, now we have, at the end of, I stop the movie again, we have now a layer of ice, thin, plus hemispherical shape of water. And if we still continue the experiments, this water spherical cap will solidify. In this very simple movie where you can understand everything, there are a lot of things which are not so obvious. First, we have seen that water is deweighting ice. And it's definitely deweighting. It's not something like the interface between the solidification front and the liquid interface that would make this move. Definitely deweights, which is definitely not a trivial consequence. You know, most of the liquid metal, they will never deweight their own solid metal. So it's probably water and few other that have this property. And so far, this is something we are working on. This is not easy to understand. So, but this is an experimental observation. Water deweight ice. Let's go to minus 30 degrees. Again, first regime you spreads, you are pinned by the contact line, and because of that you have capillary wave to relax from the maximum radius to somehow almost a flat shape of the water, and then again you retract. But now, and you can understand that also with the end, you retract, but at the same time you are also solidifying, and since you are cooler, you are solidifying faster, and somehow you may have a competition between the retraction speed and the solidification speed, and in that case, the solidification wins, and you cannot retract until the spherical cap, and you entrap somehow a ring. And finally, at minus 60 degrees, you have something which everything, it goes so fast to solidify that you don't retract, and you have something like a pancake. So we call that, I think, the fried egg structure. The other one was the donut, and the last one was the pancake. Okay. So I will not discuss too much about that, but we did some work about understanding the different shapes that you obtain at the end are these different shapes, and we'll not discuss that today, but basically we could understand quantitatively the thickness of that by using the 1D model of ice formation. So basically if you compare the thickness of this ice layer with the square root of dt, taking the time that you observe before the retraction, it works quite well. And again, if you compare the solidification speed with the retraction velocity, again you can separate these two regimes very easily. Okay. But what I would like to discuss before the end of my talk is the first part of the movies that I show you. How much does it spread as you vary the substrate temperature? And I will actually go a little bit further on that. I will also consider impact on ice, so that you can have the drop can solidify because it is on a cold substrate, but it can also melt the ice if it impacts an ice substrate. So maybe a few words about impact spreading. So there was quite a lot of activity about understanding how much, when you have a drop impact, how much does it spread. There are a lot of application in the sense if you do inkjet printing, you want to control that. You want also to make sure that it is a spherical, circular line. So basically, somehow understanding the maximum diameter of a drop that is impacting on a substrate is something that, if you want to understand well these dynamics, you should at least understand that. Basically, it depends on many parameters, and if you think about the drop diameter, the drop parameter, this is mostly viscosity and surface tension compared to inertia that should drive this spreading. And basically, as dynamical parameters, you expect that Reynolds and Weber number plays an important role, but also the material on which you do the impact, that means the wettability of the dot. There are a lot of work on that. You can make some assumption about the type of flow that you have, and you obtain two laws can be deduced. Basically, if you consider that all the kinetic energy that you have sent by the impact is dissipated through viscosity, you can get a scaling that goes like Reynolds to the 1/5. And actually, this scaling has been actually deduced by many different ways, and actually we reduce it in another way by saying, in some sense, the way you can understand this Reynolds 1/5 is also the fact that you drop, if you consider the drop impact without viscosity, so let's say the potential flow of a drop impact, it will just it will just spread, and you will have the thickness of the liquid layer that decreases as function of time. But at the same time, now if you consider viscosity as a boundary layer that grows from the substrate, there is a time at which the boundary layer of your viscous flow, the viscous boundary layer will meet the free surface. And if you just do this balance, you also get Reynolds to the 1/5, which is probably a better way to understand where is the maximum diameter. So this is a competition between viscous boundary layer and free surface, and when they meet, they reach the Reynolds to the 1/5. The other limit is maybe easier to understand. As you spread, you create new surfaces, so you have to give more energy, surface energy. If you don't consider wettability so far, it should give you like beta, so the spreading radius, the maximum radius divided by the initial radius, should go like Weber to the 1/2. So there have been a lot of experimental work on that, and actually what we have used is somehow you can rescale these two laws and to put them in a single law. Let's say if you divide this radius ratio, this ratio by Reynolds to the 1/5, and you trace that as function of Weber to the Reynolds minus 2/5, you can show that all the data that you can take from the literature collapse in a single curve, which was a way to prove that this law was probably the correct one compared to other laws. And what was nice is that it was done with a paper with Nick Lahn and a group of Daniel Bohm, is that we could collapse all the data, all the experimental data of the literature on a single curve, and this curve was easily fitted using a Paddy approximant with this thing. So the question now is what happens if you consider solidification and melting? We have this, let's say, theory of spreading. So we did two types of experiments. The first one, actually this is the last one that I will present it first, drop impacting on the ice layer. And I will show you, so I will make the impact of a water drop of an ice layer. We put some fluorescein on the drop in this case. So that means the fluorescein is, you can see the fluorescein when it's liquid, and you cannot see it when it's solid. So the drop is spreading, and you see that so you have some still water, and you have a maximum spreading radius. The question you can ask yourself, do I melt or not some ice when I do that? And actually, you can do the opposite. The water was without fluorescein, the solid was with fluorescein. So if you see fluorescein appearing, it means that you have melted some ice. And you see this nice, if you have, I can maybe show this movie again. You can see very nice instability here that I'm going. Okay. So we can again measure the maximum diameter divided by initial diameter as function now of the impacting velocity and the temperature of the substrate, temperature of the ice, and so on, temperature of the water. And we can try to maybe redo the model that we had before. If you remember, the way we were understanding the maximum diameter was to say, okay, I have a viscous boundary layer that grows from the substrate, and this viscous boundary layer, when it meets the free surface, somehow you stop the spreading, and it gives you a criteria for maximum spreading radius. If you remember, the viscous boundary layer grows at square root of t. We are lucky because you remember that the ice layer, you can say at first approximation, it's also growing at square root of t. So somehow we are lucky, or we have made everything to be lucky, so that now we can consider as first a very simplified model that instead of having only the viscous boundary layer, we have the viscous boundary layer plus the melting or the solidifying layer. Because melting, and in that case, you can say, okay, now I will just adapt my criteria when the sum of my viscous boundary layer plus my ice layer, or the sum of the difference between my viscous boundary layer and the melting layer, when that meets the free surface, it gives me a criteria for the maximum diameter. So if you just do this simple adaptation, you can put now in the same curve all the data. So the triangles are for the case without solidification and without melting. But if you add all the data we got by considering dropping pack on solid surface, dropping pack on ice, you have all these blue ones. And if you consider now the correction, that means you just correct the Reynolds number by this additional solidification layer, you basically, you are able to put all your data on the same curve. We have maybe a little bit more of error bar, but it's still very good. Okay, I might stop there. Maybe I will just finish without going into too much detail about something that we observe also, which is to continue on this dropping pack and solidification. What happens about splashing and spreading? As you know, another thing which is important when you dropping pack is whether you will have or not splashing. It's important also, again, for inkjet printing and for a lot of other processes. And the question we ask is, does it change something if we impact on a cold surface compared to a regular surface? And you know that we can define, if you do freeze it, you have a nice spreading here, a nice splashing here. So we can define splashing as soon as you have a drop that is ejected. And maybe I will not discuss that, and to show you what we have observed is definitely something interesting. The same drop impacting on a room temperature substrate is definitely spreading, and at the same velocity, everything the same except the substrate that is at minus 55 degrees. You have a nice splashing. So definitely, cold substrate make splashing easier. And if you look to this curve, we can show as function of the velocity and as function of the temperature of the substrate, you can see that there is an evolution of the velocity as function of the temperature. And we use actually the theory of Ribot and Gordillo to treat this data, particularly in this regime. And maybe just to make it a long story short, I will just concentrate about why at a very low temperature we have splashing, and somehow what we have is a clue and not an explanation. Let me go fast. If now you do the same impact, the same drop on a super hydrophobic surface, for the same velocity that was spreading for room temperature and splashing at very low temperature, you see splashing if you are at super hydrophobic. So the conclusion is that somehow a cold substrate behaves like a super hydrophobic surface. And the idea is that the substrate does not care about being below zero or above zero. It does not change anything for a metal. On the other hand, maybe the liquid that is approaching such a surface might have some crystal that grows at the surface, and somehow it might not be the substrate that becomes hydrophobic, but maybe the water that becomes surface phobic, to make it like a joke.
Are the splashes liquids or are they ice?
We think they are liquid,
Okay.
but we haven't checked. I think that's the correct answer. We think they are liquid because there is nothing they detach from it, but we haven't checked. Okay, and I will just go to my conclusion. So we use the mechanism of Gordillo. And, maybe I will put some perspective on this work. So basically, we have looked at drop dynamics, how it is affected by solidification and melting in terms of maximum spreading and splashing. We have seen all these things. Maybe I would like to just make some perspective of what we are working on these days. As you have seen, there is something which is quite intriguing, which is that water de-wet ice. you can see that, and this is not an easy problem because weighting property should be done at thermodynamical equilibrium, and when you have phase transition, it's not so clear what is thermodynamical equilibrium. And basically, we are working on contact angle to really try to determine what is the contact angle of water on ice, particularly at 0 Celsius degree and so on. And also, we are working on more complex systems like rivulets flowing down a cold substrate and so on. And I think it's time for questions. Thank you very much.
Thank you for a nice talk. Fabian has a question.
Fascinating work. You mentioned towards the beginning of your talk that the growth rate of the ice depends obviously on the substrate or how much heat is taken away through the substrate. How do the solid properties come into all of this? I don't think you've mentioned that.
No, I didn't mention it, but maybe I have some slide where I can show that.
Because I would guess on a different solid, things will change, right?
Sure. Let me try to get that somewhere. Okay. So basically, maybe I can draw that.
I think on the main plot, like with the diffusion coefficients, there are several cases.
Yeah, but maybe to make it okay. So you have your substrate. Here you have your ice. Here you have water. So in your 1D self-similar solution, what is interesting is that this temperature is a contact temperature, which is you find it easily from your solving your self-similar solution. And it's very interesting to understand what is this contact temperature. This is exactly the temperature you would get, let's say, if I do that with my finger and that. My feeling is that that is cooler than that, which is not true. They are all at the room temperature. And the reason is that the metal is able to absorb heat much easier, and this is related to what we call effusivity. So in this contact temperature, which drives somehow all the thermal flux after that, there is the effusivity of ice, for instance, which is basically the square root of the density, I think basically the diffusive and the capacity. So which is important, this is a combination between how you can diffuse, but also how you can store energy. And this is really what so that's how it enters, and then all the flux and all the dF that we have is depending on that. So effusivity of the material is crucial.
Thanks, very nice results. Very curious about something. So whenever I do droplets on any surface and I need to clean the surfaces, which is quite of an important thing, I tend to scratch them. And in your case, I'm not going to ask if how they're cleaned or how they're scratched or any of that. Have you considered roughness?
Graphens?
Roughness.
Roughness. Okay. Okay. Many answer about that. So you're right. Roughness is crucial for splashing, particularly. Splashing. So that's one of our ideas that maybe because when you are very cold, you may have some ice crystal, frost crystals that might do. So that's we haven't make really. We don't really know whether it plays or not a role. On the dropping pack, on the spreading, as you may have seen, we have other movies where the surface is definitely scratched by many reasons. It does not change that. So we haven't seen a huge effect on the spreading itself. For the splashing, I wouldn't be as affirmative. For the spreading, it's in the experimental error.
Would it be worth checking something where, wicking action and have something like that when it spreads, when it impacts and spreads very rapidly to avoid icing?
For instance,
not to avoid, sorry, to delay. You cannot avoid.
Maybe I will answer in a different way. Some colleagues did the same experiment as us, but with a very, very clean and very, very smooth surface, which is somehow, and then they had a lot of metastable situation where the drop was spreading without solidifying, and then suddenly solidifying. Somehow we made something in purpose, not that control. In order, we wanted to, somehow the realistic case are normal surfaces where you have a lot of roughness or small things that can create seeds for crystal. Somehow how the first layer of ice is forming is not considered here. There are some work actually by the group of Loser about how they nucleate and how they spread. Somehow we are looking to the dynamic just after that. But you're right. If you have a very, very smooth and clean surface, you may have a delay just due to this metastable situation until. And somehow we have avoided that in purple.
Yeah, hi Christophe, that was a great talk, thank you. You mentioned Reynolds number to the 1/5, which is a fascinating power. What sort of range of Reynolds number does that cover?
Actually, this is the law which is maybe the more observed. It's few hundreds, let's say. Until few hundreds. I'm not sure it goes good. Because the problem you have somehow, if you want really to adapt to that, you want to avoid splashing. So you cannot be at too high Reynolds number because after that you have splashing. It does not vary a lot for the spreading radius, but still it changes a little bit. So it does not go to very high Reynolds number.
Any more? Okay.
Do you estimate the heating due to the viscous shear in the boundary layer?
No.
Do you think it's negligible?
Well, we haven't computed it. We are probably something that might be more than that is we neglected also the air, interaction with air, particularly in Toulouse. They have made experiments with controlled humidity where if you have a lot of humidity, then you have water that can condensate on the drop, and actually the latent heat of vaporization is even higher than the latent heat for solidification. So, but no, we haven't considered that. No, I couldn't say. Like that, I would say it should be negligible, but we haven't computed.
Cool. Oh, there's. We still have time, so if you're happy to.
And actually,
answer
I
questions
keep
or-
time because I wanted to show something for Sasha.
Well, Sasha has a question too. So.
Thank you very much. Once the impact and solidification finished, you can study the ice. And ice, I believe, is different depending on the impact conditions. Right? It could be kind of amorphic, very strong ice, or porous. So what's the type of ice in how it depends on the impact conditions.
So it's interesting. As soon as we started to work on that, everybody warned us not to do ice because water is so complicated and so on. And many people say exactly that there are many different types of ice. Usually different type of ice, in terms of, let's say, crystallization, you need very high pressure. So we are not in this situation. But where you are right is we may have sometimes some bubbles entrapped. The starting of the ice front is very rapid, and you may have some dendrites that entrap water. So sometimes you have, let's say, a very transparent ice. Sometimes you don't have a transparent ice. It depends on that. But we haven't seen effect. On the other hand, we haven't seen crucial effect because of that. So the experiments are very well repeatable. So even if it can be there, it's not an important role what we are looking at. And probably what we don't have is different type of crystal of ice. We may have different state of ice, sometimes with more dendrites than homogeneous growth. But we haven't seen a crucial effect of that. That's true. It should be careful about it.
Okay.
And if you give me 1 minute, so Sasha asked me that he heard about the question where was coming the name of Ladix, and I don't want to say that, but there is somehow an analogy with today. So Ladix, there is a comics in France called Bug Danny. I'm not sure it's known otherwise. So it's a comics, and there was a famous. So he's a plane pilot. And he had sometimes he had some and there was one of the comics was Bug Danny against Lady X, and Ladix is Laboratoire d'Hydrodynamique de École Polytechnique, and École Polytechnique is often called X, so that's why we use that. And so Rodolphe Grivet found comics where Bug Danny actually had a problem with ice on his plane. So that's the connection with today. Okay.
Well, let's thank Christophe again for the nice talk.